Okay, so Hardy-Weinberg is a bit boring. Nothing's going on, no evolution is happening. What happens if we monkey around with some of those assumptions? First of all, monkey around with the assumption that there's no selection going on. Right, the first concept we need to define is fitness, because it relates to selection. Lifetime reproductive fitness is symbolized by W by convention, and we want to describe the lifetime reproductive fitness of a genotype like the one carried by Mildred. And we remember her life history. She meets George, they have children. They have 3 children, so maybe their reproductive fitness or her reproductive fitness is 3. But what matters is whether those children go on to have families of their own. And in this case, only 2 of the 3 children do that. So by definition, the lifetime reproductive fitness of Mildred's genotype is 2 and not 3. So let's think of the different genotypes that are available with the model we've been talking about. Gene A with 2 alleles, A1 and A2. There are 3 genotypes, 2 homozygotes and 1 heterozygote. Each of them has a lifetime reproductive fitness, which we are going to call W11 for the homozygotes, carrying 2 copies of allele A1, and so on. The first thing we need to know to calculate is the average fitness of the population. This looks at first a rather scary equation. Several of these may look a little scary at first, but actually, if you take a little bit of time, they're all very simple. This one is simply saying that the average fitness of the population is the average fitness of the genotypes in that population weighted by their population frequency. So let's just take the first term, P1 squared, that's the population frequency of the A1 homozygotes, multiplied by W11, that's the fitness of the A1 homozygotes, and so on. Simple. Let's then have a look at Genesville, where all those happy individuals were busy producing the next generation. Under Hardy-Weinberg conditions, nothing much was going to happen. But when selection intervenes, maybe allele frequencies will change. So let's assume, in this case, that the genotypes have the fitnesses shown on the slide here. And this is an example where the A2 allele is a recessive lethal allele. So in the homozygote A2, no reproductive offspring are produced. Fitness W22 is therefore 0. But in the heterozygote, the recessive allele is not expressed and it looks exactly the same as the homozygote wild type, and the fitness W12 is the same as the fitness of W11, equal to 1. Okay. Remember the first generation, the starting point, just like in the last podule, the frequency of the 2 alleles was equal 0.5. What happens if the fitness of the homozygote A2 is 0, as shown here? Well, first of all of the homozygotes disappear from the reproductive pool, effectively. Did you see them disappear? Let's see them do it again. They all disappear. And now we just count up the alleles that are left in those individuals that successfully go on to contribute to the next generation. And we see that the allele frequency is now very different. The frequency of the A1 allele has gone up from 0.5 to 0.66. That's from half to 2/3. And the allele frequency of the recessive lethal allele has gone down from a half to a 1/3. We can calculate that algebraically by saying the frequency, this equation says the frequency of the allele in the second generation is equal to the frequency at which its alleles are found in the first generation multiplied by the fitness of each of those genotypes divided by the population fitness. Just note there that in the heterozygous case has only 1 copy of the allele A1. So it isn't 2 times P1 times P2, it's just P1 times P2. So given that the alleles have changed so dramatically in frequency, what happens to the genotype frequency? Well, you remember when the alleles were equally frequent, the genotype frequencies were 1/4, 1/2, 1/4, like this. But when the allele frequencies change, as we saw in the last slide, we can use the usual Hardy-Weinberg equation to calculate the genotype frequencies. And when we do, we find that the frequency of the genotype, the homozygous wild-type genotype, has gone up from 1/4 to 0.44. The frequency of the heterozygote has gone down a little from 0.5 to 0.44. And the frequency of the homozygote carrying the recessive lethal allele has dropped very dramatically from 0.25 to 0.11. Now that change in allele frequency over one generation can be calculated algebraically. So delta P1, that's the change in the allele frequency of allele A1, equals the allele frequency of A1 in the second generation minus the allele frequency of A1 in the first generation. And we've already seen what the allele frequency of A1 is in those two generations. It's given by those two expressions just there. So we can simplify those a little bit. We could multiply the minus P1 element, the minus P1 element by W bar to bring it all into one neat expression like that. And then we notice that there's a W bar on the bottom and a P1 on the top of each of those components, and we can take that out of the expression and simplify it in that way. So that's the way you can calculate the change in allele frequency generation by generation if you know the fitness of the genotypes and the population otherwise obeys Hardy-Weinberg rules. Or we can let a spreadsheet program like Excel take the strain. Now in this model, which you will find on the site, we can change any of the values in the yellow boxes, and in this case I've simply changed the value of the fitness of A2 homozygotes, that's the one carrying 2 copies of the recessive lethal allele, to 0, leaving the fitness of the other genotypes at 1. Starting frequency 0.5, and you can see there's a very rapid change in the frequency of the two alleles as the generations run. We're looking at 100 generations changing on the x-axis here. So this tells us that for a recessive lethal trait of the sort we've been looking at here, there's a very fast reduction in the frequency of that allele at first, but as its frequency drops, the rate at which it drops away falls. And that's because at low allele frequencies, most of those alleles are present in heterozygotes whose fitness is just fine. And it's only when that allele combines rather increasingly rarely to produce homozygotes are they exposed to the force of selection and eliminated. So the elimination of the lethal genes from the population becomes asymptotically slow as it gets lower and lower. Now that's just one example. That's when we've got a recessive lethal allele, A2. But we can use all of those same equations and we can use the same spreadsheet to calculate what would happen under different circumstances. So for example, what happens if A2 is dominant lethal? That is, it's lethal, its fitness is 0 in both the homozygote and heterozygote case. What happens if the allele A2 is partially dominant but not completely lethal? What happens if the A2 allele is recessive lethal but the heterozygote has a selective advantage over the wild-type homozygous? Now you can do this in 3 ways. You can either go away, use the equations you've seen in this module and calculate for yourself what will happen, or you can play with the spreadsheet, or you can watch the 3rd module, or you can do all 3. See you later.